All right, we're on example 8. It says to simplify the following using the change of base formula. This is a product of 4 different logs, and if you notice, they all have different bases, right? 3, 2, 7, 5. So this is just some number, so it's going to equal some number in the end. We just want to make it look a little less intimidating. Maybe fewer factors, fewer logs, fewer numbers. It said there's a hint up here of how to do that using the change in base formula. So if you remember what that was from way back yesterday ago, that says that you can take any base that you'd like and convert the base you're given to that base by taking the log of your new base, we'll call it A, of the old argument over log of your new base of the old base in the denominator. When we're trying to evaluate it, we'll typically change them to base E with the natural log. But that isn't necessarily going to help us here, but it might. So anybody have any ideas then what we could do? Should we make them all base 3 or all base 2 or all base 7 or all base 5, or should we convert them all to some third-party base? I guess it'd be fifth-party base. How about this? I'm not sure if this will work. Can we just take the log of all of the arguments, 5 times 7 times 3 times 11, and say it's to the base, that's the product of the bases, 3 times 2 times 7 times 5? You think that works? That's just doing something with the numbers arbitrarily, right? Does that generally work? Just doing random stuff with numbers? No, that's not the way to do it. What if we put them all in terms of the same base? Then we know, since the change of base formula generates a quotient, when we have factors that have numerators and denominators, we then have the potential of dividing out factors from high to low, right? So that might be the strategy. So pick a base, any base. What base should we convert them to? We have 4 bases up there, 3, 2, 7, 5. 2, you want to choose 2? All right, 2 it is. See? It's a democracy. We're going to change them all to base 2. I'm in base 2. All right, so log base 3 of 5 in terms of base 2 is log base 2 of something over log base 2 of something. What goes in the numerator? The 5 or the 3? The 5, and then the bottom we get 3, right? So that's that one. Times. Hey, this one's already in terms of log base 2. How nice is that? That's a rhetorical question. You don't have to answer. It's real nice. All right, and so the next one, log base 7 of 3. That's the same as log base 2 of something over log base 2 of something. Is it 3 over 7 or 7 over 3? Yeah, it's a silly question. Give a silly answer, right? 7 is lower than the 3 in the structure of the log notation, so it's actually lower in the quotient. And then the last one, kind of doing the same thing, log base 2 of 11 over log base 2 of 5. So now at least we have like the proverbial apples to apples, if you want. We can only divide out factors if we have the same factor in the top as we do in the bottom. Then they divide out to give us 1. Do we have any factors that are the same in the top and the bottom? Yeah, quite a few actually, right? So let's go ahead and find them. I've got a log base 2 of 5 here and here. So those divide out. Even though they're not next to each other, they're about as far away in that expression as 2 factors can possibly be. The associative property allows us to divide them out. Here's a log base 2 of 7. See ya, wouldn't want to be ya. And then the log base 2 of 3s, adios, muchachos. And we're left with log base 2 of 11 over 1, which is log base 2 of 11. And that's pretty simplified, isn't it? Yeah. Now, if you wanted to evaluate that on the calculator, of course, you can either go to your F2 menu and type in the base 2 in the box, or you could just convert it to natural log. Natural log of 11 over the natural log of 2. So there you go. Yeah. You're going to have several options on these problems. You don't just want to sit there and look at it and be paralyzed by indecision. When in doubt, just go for it. Just do something. Would it have worked if we had chosen A different base? Or did we just get lucky and choose the right one? Well, there's only one way to find out. Bless you. Let's do it a different way. Let's do it a different way. We'll call this method 1. Method 1. All right. Let's get crazy here and actually choose a base that's not even in this expression. We have bases of 3, 2, 7, 5. What is a number that's legal that's not a 3, 2, 7, or a 5? An 8. Bold choice. Let's convert them all to base 8. Convert to base 8. I was hoping you were going to say base E, because that's the one we want to kind of tend towards when in doubt. But you said 8, so we'll do it. Good luck. Log base 8 of 5 over log base 8 of 3 times log base 8 of 7 over log base 8 of 2 times log base 8 of 3 over log base 8 of 7 times log base 8 of 11 over log base 8 of 5. Whew, that's a lot of writing. ln is a lot easier to write. I wish you would have said E, but you didn't. And again, I'm not trying to rub it in or anything, but okay. Does anything divide out? Log base 8 of 5, see ya, wouldn't want to be ya, right? Log base 8 of 7, adios, muchachos. Log base 8 of 3, bye-bye, bye-bye. And that's all that divides out. So we're left with log base 8 of 11 over log base 8 of 2. So that simplifies, but is that as nice as the way we had it earlier? No, because now we still have 2 logs and we have a quotient. So maybe at this point we could try to simplify even further by doing, let's do the natural log now. Let's try the natural log. What base do you want to choose? E, they said. Let's put them in terms of base E. That's the natural log of 11 over the natural log of 8, all divided by the natural log of 2 over the natural log of 8. And of course, then we could stay, change, flip. Natural log of 11 over the natural log of 8 times the natural log of 8 over the natural log of 2, and the natural log of 8's divide out, and we're left with the natural log of 11 over the natural log of 2, which again is really not any better necessarily than what we had over here. We still have a quotient, we still have 2 logs, but now they look cuter. They're ln instead of log base 8. And of course, if you compare that answer there to the other version that we had here, they are equivalent. So yeah, it is nice if you actually convert all of these to one of the bases that's already there. It'll simplify down to just a single log. But if you put everything in terms of base E or base 8 as we did, that's fine too. This would probably show up on a multiple choice answer, and so you're going to have to look at your answer choices to help inform you as to what base to convert it to. If all of your answer choices are in terms of base E, maybe you put it all in terms of base E to start with. All right, kind of fun, right? Kinda? Emphasis on kinda or emphasis on fun? Kind of fun. Fun, right? Kind of fun. Yeah, it's actually kind of fun instead of kind of not fun. Instead of like kind of fun instead of like a lot of fun, right? We always emphasize the fun and not the kind of. Yeah. Right, function, fundamental. Oh, she's in the waiting room. Yeah. Yeah, the doctor will be with you shortly. All right, so now we're ready to jump to example 6. We're going to solve logarithmic equations, which, you know, we already kind of did, up here on example 1. It said to solve. But on example 1, it was really already solved for x. It was x equals a number. We just simplified the number. In this example, we are going to solve for x, or I'm sorry, in this case it said z. I got crazy and chose z. The expression is not already explicitly solved for z. We're going to have to get to z. Z equals something. All right, so log base what of z equals 3? What's the base there? Did I forget to write it? It's 10. I didn't forget to write it. All right, so all right, so let's see. We know that God, I don't know what the answer. Anyone? How to start? Guess and check? Let's think about it. We want to unlock the z, right? The z is currently trapped behind a log base 10. So if we can undo logging base 10, we can free the z, right? Free the z. Free the z. What is the inverse of logging base 10? Exponentiating base 10, which is the same as converting it to exponential if you like to travel around the world. But I'm going to go ahead and do that. 10 to the blob on the left equals 10 to the blob on the right. Now on the left, 10 to the log base 10 of z is just z, and we're left with 10 cubed. And of course, what is 10 cubed? 1,000, right? So that's the systematic algebraic approach, right? Apply the inverse operations, peel back the layers until you get to isolating the variable of interest. Now, you want to get in the habit of checking your answers. Whenever you're solving for logs, you want to get in the habit of checking your answers. Because sometimes, algebraically, in the process of solving, extraneous solutions can work their way into the answers. And extraneous means that they're extra and don't work. So how do we check our answer? Well, remember, we can only take the log of a positive number. So if you take your answer, which is 1,000, and you plug it back in for z, which is in the argument, when you do that, do you get a positive number? Yeah, 1,000 is a positive number, so you know it's going to work. All right? But you'll see sometimes that, and we'll get to those examples, where they don't work, and you have to cast them out. So just kind of develop the habit of quickly checking your answers. Plug them back into the argument. Does it give you a positive result? If so, it's good. If not, throw it out. All right, so that was pretty easy to start with. Over here, we got kind of the same thing, but now it's log base 2 instead of log base 10. The variable is trapped inside the argument. We need to free the z plus 1 now by unlogging it base 2. How do we do that? Yeah, the word is exponentiate base 2. And I'm okay if you do it on the same line if you want. The left side and the right side now become exponents on the 2. And then on the next line, of course, 2 to the log base 2 of blob is blob, because that's inverse operations simultaneously. And then we get 2 to the 4th. And now it's like you're back in an Algebra 1 class, right? We've turned it into a linear equation, z to the 1st instead of x to the 1st. So let's go ahead and solve it. 2 to the 4th is 16, good. Subtracting the 1, you get 15. So you don't even have to show the minus 1 on both sides, you know, like you did in Algebra 1. If you still want to, that's fine. But a little bit of agility in solving these things and not showing everything, you should try to work towards that. All right, so now we just got to check. Does 15 work? Well, when I plug it back in right here, what's 15 plus 1? Positive, who cares? Is that what y'all said? Y'all said 16, but y'all meant positive 16, right? You could actually say positive, who cares? Because we know we did the math right. We know it's going to work if it's not extraneous. And it's going to work if it makes a positive in the argument. And it does. All right, you do this one on your own. Ready, set, go. You exponentiate both sides to the 1/2 power, like I did. The left side, you get the argument, 2z plus 3. The right, you get the quantity 1/2 to the 5th. Now, notice I put the 1/2 in parentheses. It's better when you have an actual rational number that's as a fraction to put it in parentheses. Because without, if you just wrote 1/2 to the 5th, that 5 is kind of now uncomfortably far away. So if you bring it in closer, it looks like that. And that's either going to be interpreted as just 1 to the 5th over 2, or it could be interpreted as 15 over 2. And you don't want that to happen. So when you have a numerator and a denominator raised to a power, get in the habit of just putting in parentheses. But anyway, 1/2 to the 5th is 1 over 32. And now I saw a fraction and I panicked. That's why I put yikes and eek. I'm not sure what to do from there. So we have two options. You can either continue working the problem with fractions, that is, embracing the fractions, or you can eradicate the equation from the fraction and work it without fractions. So one of them is embracing the fraction, the other one is like excommunicating them, the opposite of embracing them. What do you want to do? If you're afraid of fractions, which one should you do? No, you should embrace it actually, right? Face your fears and your fears go away, all right? So let's go ahead and do that. Let's work with the fraction. I'm going to subtract 3. And notice I put a line through my z's because without that they look like 2's. So I get 1 over 32 minus 3. Okay, here we go. Here's the moment of truth. All right, fraction, you're not going to get the best of me today. If I take the 3 over 1 and multiply by 32 over 32 to get a common denominator, what is 3 times 32? 96. Hey, that wasn't that bad. What's 1 minus 96? Negative 95, right? So I get negative 95 32nds. And now you can divide both sides by 2, which is the same as multiplying both sides by a half. So I end up with negative 95. Then when I multiply by a half, the 32 times 2 turns the denominator into a 64. That wasn't bad at all. That wasn't bad at all. Now let's plug it in and see if it works. Plug it back in. 2 times that is negative 95 32nds plus 3. Well, is 95 32nds less than 3? Yes, by 1/32 it is. Wow, barely. But then when you add 3 to it, it's going to be a positive number. So it actually works. It does actually work. So that's one way to do it. The other way to do it from here is to eradicate the fractions. If you do that, you're going to have to multiply both sides by 32. So if you do that, you distribute on the left side, you're going to get, let me show it. You get 32 times the quantity 2z plus 3. And now on the right side, you're left with 1. So if you distribute then, you get 64z plus 96 equals 1. And so notice there's no fraction. So you get 64z equals negative 95. And then you divide through, and you get negative 95 64ths. So you get the same answer. It's just entirely up to you. If you want to clear out the fraction on an equation, you just multiply both sides by the LCM of your denominators. And it makes for a little bit easier, and at the end you'll get the same answer. So again, if you're afraid of fractions, don't avoid fractions. Work with them, get good at them so that you understand them, and then you're not afraid of them. All right, so those 3 examples had the unknown in the argument. Cool. There are other locations for unknowns, like this one. This one has an unknown what? What do we call that, the subscript? The base. Yeah, this one has an unknown base. So we know that there are certain bases that are allowed. We can either have them between 0 and 1 or greater than 1. The base can't be 1, 0, or negative. So if we end up with a 0, 1, or a negative answer for z, we're throwing it out. Okay, what to do? Right now, the z is trapped inside the log as the base. How do we untrap it? What is the inverse of logging base z? exponentiating base z. Yeah. So let's go z to the that equals z to the that. Now, on the left, what is z to the log base z of blob? It's just the blob in general, which is 25. And on the right side, we get z squared. That's a quadratic equation. We're either at the end of Algebra 1 or the beginning of Algebra 2. So we can solve that by extracting square roots. And whenever you extract square roots, that is, take the square root of both sides, you have to at least consider what? Both plus or minus. You got to consider both. So that would be plus or minus the square root of 25, which is 5. Now, once you've considered both, if you box them both up and walk away, unfortunately, now you're going to lose points. Which one does not work? The negative 5, because we can't have a negative base. So notice there was nothing quadratic about this to begin with, but it turned into a quadratic. That's when you have to be really careful about possible extraneous solutions. If you take something that's linear and you turn it into a quadratic, linears can only have one solution. Quadratics can have two, and one of those might be extraneous. So once you consider both, and I do want to see that you're considering both, how do you declare that you only want the 5? It's as easy as underneath they're just saying z equals 5. That's it. That shows me that you've considered both, but then you've excluded the negative one. If you want to even like make it more obvious, you could say z equals negative 5, and then you can go cross it out. And sometimes it's fun to cross things out, right? Like when you get your yearbook and you go through there and you say, I didn't like that person, so you draw an X over their face, right? And then you look back to your yearbook years later and you're like, you know what? That guy wasn't so bad. I wish I wouldn't have done it in pen. You know, we're actually best friends now. True story. Middle school. All right. All right. Any questions on that one? All right. So then the other place where you can have the unknown, if it's not in the argument or it's not in the base, it's going to be on the other side. And we've already seen those types of equations. This was like the earlier example. You have z equals, it's already solved for z. Z equals this. But that is a number that can be simplified. So go ahead and do that one on your own. Simplify early and simplify often. Good. That's it. Close. Close. Real close. Yes, Maru. That's not quite right. All right. The first thing I'm going to notice here is that I have a quotient 5 over 125. And since 125 ends in 5, I know it's a multiple of 5. So the first thing I'm going to do is simplify 5 over 125 by dividing out of 5. And I call that then 1 over What's 125 divided by 5? 25, right? That makes it a little bit easier. And now, as we already saw, if you're evaluating it, if the base is 5, now if you can write the argument as a power of 5, you'll have it. So whether you keep it as 5 over 125 or simplify first, it's really the same process. That's the same as 1 over 5 squared. And now I'll bring that to the top. And when I bring it to the top, of course, the 2 on the exponent becomes a negative 2. And now I'm ready to evaluate it. I have log base 5 of 5 to the blob. In general, then, it's equal to the blob, negative 2. So at some point, you're going to have to combine either the exponents on your powers of 5, because you could have written this as 5 to the first over 5 cubed. And then you would simplify that to 1 over 5 squared. So at some point, those simplify. If not in the beginning, you could do it at the end. But the answer is negative 2. So there you go. Inch by inch, it's a cinch. All right. That concludes page 3 of 5. Any questions on the first 3 pages? All right. How many pages to go? 2. Good. Good. That's a good math problem. All right. So now we're going to start looking at the graphs of the log functions, which, of course, we know that a log function is the inverse of some exponential function. And to get the graph of an inverse, as we've already seen, you reflect it across the line y equals x. So let's look at this graph here first in blue. That is building on what we've previously learned. This is the exponential function of the form b to the x. For the base greater than 1, that means it's exponential growth. It passes through the point 0, 1. It also has a horizontal asymptote on the y-axis. So if you took that graph and reflected it across the line y equals x, the point 0, 1 turns into the corresponding point known as 1, 0. The horizontal asymptote on the x-axis becomes the vertical asymptote on the y-axis. And every other point then reflects across perpendicular to the line y equals x, and you end up with that red graph, and it is now of the form y equals log base b of x instead of b to the x. And notice they're both increasing, aren't they? So if your base is greater than 1 for exponential, you know it's exponential growth. It turns out for the base on the log, if it's also greater than 1, it's called logarithmic growth, or just log growth versus log decay. So that's the same as it is for exponentials. But there is a noticeable difference. Exponential functions, as you go out to the right, go to infinity at an increasing rate, very, very fast. The log functions, as you go out to the right, still go to infinity, but at a decreasing rate, very, very, very slowly. And that, again, is what logs do. Logs bring huge numbers down to smaller numbers. They make growth manageable, okay? So that is your parent function right there. For any log function now that's growth, for the base is greater than 1, they're all going to have the same property. The vertical asymptote's at x equals 0. The domain is everything to the right of 0. The range is all real numbers. They're going to be monotonic increasing, and they're going to pass through the point 1, 0. Everything of that form. Now, what if you have a bunch of log growth functions on the same graph? Like we did with the exponentials, there is a hierarchy to how fast they grow. Remember, for exponentials, the bigger the base, the steeper the graph. So like 10 to the x grew faster than 9 to the x. For logs, let's see if it's the same thing. The resolution is kind of bad here, and I apologize for that. This is log base 2, this is log base 3, this is log base 5, and this is log base 10. And they're all of x. Which of those graphs is the steepest? Log base 2, right? Which base is the smallest? 2, right? So if exponential growth functions grow according to the bigger the base, the steeper the graph, The log functions, which are the inverse, we can't say the same thing. We could now say, though, the smaller the base, the steeper the graph, instead of the bigger the base. Or you could say the bigger the base, the less steep the graph, or the slower the growth. The bigger the base, the slower the growth. That makes sense as well. And what's common, though, among those different bases is, again, they all have vertical asymptotes. Let's go ahead and write that. They all have vertical asymptotes at x equals 0. They all have x-intercepts of 1, 0. Let's list the domain. The domain then is going to be the set of all x such that x is strictly greater than 0. And the range is all real numbers. Now, it works very, very similarly for logarithmic decay. The only difference for logarithmic decay is that you just take these and reflect them across the x-axis. Okay, and that's going to be if you have the base between 0 and 1. So you do need to know the hierarchy of growth within the family of logs based on their base. All right, let's jump to example 7 then. Now that we know kind of this new family of parent functions, we could do what we've been doing with every function so far. Sketch transformations of them. And you have a lot of experience already with the natural log of x. These are going to be very similarly done. They're just not base e. So f of x equals -2 log base 3 of x plus 4. What's the parent function? This is a transformation of what parent function? Natural log of x? Log base 25 of x? No, it's a transformation of log base 3, right? Log base 3, which is logarithmic what? Growth or decay? The base is 3, that's bigger than 1, it's logarithmic growth. In fact, if you're only sketching it by itself, it looks a whole heck of a lot like the natural log of x. You don't have to actually show the steepness until you graph 2 on the same graph, and then you have to show relative steepness. So there you go. It's almost like we're sketching a transformation of ln of x. Is this then in standard transformation form? It sure looks like it, right? So let's go ahead and just talk about what's going to happen to this graph. The negative out front is going to be a reflection across the what axis? The x-axis. The 2 is a vertical stretch by a factor of 2, and then the plus 4 picks the graph up and moves it left 4. So we can go straight to the final answer. Left 4, I'm going to call that -4 and put my vertical asymptote there. Is it going to be an increasing or decreasing function? The parent function was increasing, but if I take that and reflect it across the x-axis, now it's a decreasing function, right? Decreasing. So I'm going to draw it like this. Oops, maybe not like that. Maybe like this. There we go. This one will go to negative infinity as you go to the right. Now, the one thing that we always need to be aware of, if we cross the y-axis on our graph, we need to make sure we cross the y-axis in the correct place, above or below. I drew it crossing below. How can we verify if it's supposed to be above or below? Can we find the y-intercept by the equation? Yep, and you show it by plugging in a 0. So let's do that. F of 0. That's -2 log base 3 of 4. What do you know about log base 3 of 4? Is it positive or negative? It's positive, right? It's 1 point something. 3 to the 1 point something power is 4. Because 3 to the first is 3, which is too small. 3 to the second is 9, it's too big. So log base 3 of 4 is 1 point something. What's 1 point something times a negative number? It's negative, right? So that's all you need to know. This is a negative number. Is my graph correct then? Yes. I have it crossing in negative lane. All right, so the domain. What's the domain of this function? The set of all x such that x is to the right of -4. Yeah, it doesn't equal -4. It's strictly to the right of. The range is an easy question for logs. It's the same question really as the domain of exponentials. The domains of exponentials were all real numbers. Since these are the inverses, now their range is all real numbers. all day long. Okay, here's a way to algebraically check the domain. We'll throw this in right here. To find the domain algebraically, which is kind of picking up where we left off earlier when we did it. Let me spell it right, algebraically. So there's now three things we're trying to avoid for non-piecewise functions. Can't divide by 0, can't take square root of a negative or fourth root of a negative, and now we can only take logs of positive numbers. So all you have to do to find the domain of a log function is take the argument, that's the thing you're taking the log of, and say it's strictly greater than 0, and then solve. So let's see if we get the right thing here. Our argument is x plus 4. I'll say it's greater than 0. That's a linear inequality. Can we solve linear inequalities algebraically? Yes, we can. I'll subtract the 4 from both sides, and I get x is greater than negative 4. If you compare that to the domain you got graphically, they should be the same. If they're not, you made a mistake somewhere, either in finding it algebraically or maybe in the graph. Maybe you reflected it across the y-axis instead of the x-axis. So I would encourage you to always check to make sure that you have the right graph. It says find y-intercept domain range and determine any end behavior. Okay, last thing for the day. Let's look at the two limits that make sense here. The limit as x goes to infinity on this function is what? Hop on the graph and go out to the right. We're getting closer and closer to. Yeah, this graph goes down forever at a slower and slower rate, but it does go down to negative infinity. Does this graph even have left-end behavior? Left-end behavior means at negative infinity. No, it doesn't. It doesn't have left-end behavior. But we can answer this question. What is the limit as x approaches negative 4 from the right-hand side of negative 4? Hop on the graph, start heading towards negative 4 from the right-hand side. What are the y values approaching? They're going up, 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 up to infinity. And remember, that's the definition of a vertical asymptote. If at a specific value of x, your limit is either plus or minus infinity, there's a vertical asymptote there. Okay, we'll stop right there. You got about a minute left. We'll pick up tomorrow with 7b. So make sure you're working on your worksheet a little bit every